Do you see?
Yes, I do.
Okay, okay. So sorry guys for this problem. Thank you for mentioning it. And basically, as I was just started, I just wanted to show you like two matrices, as you see, two square matrices, just with brief mathematical reminders. Matrix A and matrix B, and we are going to multiply matrix A to matrix B. I said it is like a square matrix in our case, which is like, as you see, like 2 by 2 or 3 by 3 or 4 by 4. So as you know, for multiplying matrices, we get the row from the first matrix, we get the column from the second matrix. And what do we do? That the first item of the first row to the first item of the first column. So these two multiply together, plus these two multiply together, and the summation of those will be put here. For this, for example, for the right one, again, the first row, this time to the second column. For again, for this item here, this row to the first column, and for this one, sorry, for this one, again, this row to this row. Okay, so each item of row and column will multiply together, and summation of those will be added and goes to the corresponding cell of the matrix. So uh, that's what I wanted to say about, like, basically about what do I mean by matrices, and we will go to our example. Okay, so uh, we will start with our logging to our like server, or if you are using your own Cuda, that's fine. So I started with from the scratch with the basic like empty project. As you see, this is the first thing is our Cuda check return, which we said we are going to put in all of our codes. And then we are going to start with a simple, let's say, main function, which is for now saying like hello, just something. For the sake of being easy, because I don't want to every time put std like colon c out. I'm going to use a namespace here. So using namespace std. So from now on, just the basic c out will be enough. Okay. So we have, so basically let's try to create a basic matrix multiplication. So at first, as you know, as I said, we have, let's say we have three matrices, right? Matrix A, matrix B, and matrix C, which is our result. We are going to multiply matrix A to matrix B, let's say. Okay. Um, and let me start with the simple, like what we are going you were using to and what we are going to do now. Even I remember last week I have some questions about how memory allocation, like dynamic memory allocation, like means in CUDA, and what's the difference of this one between the normal C, let's say, arrays. Okay, so that's why I put like a simple, like on Google, of course, like a matrix multiplication in C, like normal C. You know, if you remember, I hope you have done it like in your let's say bachelor or something. So for multiplying matrices, we usually need three loops, and we have, for example, a matrix, and by saying I and J, like we are moving to the different cells of the matrix. Like let's see once again. Let me put it here and like this. So okay, so like I'm not going to teach about C, of course. This is for the previous. It's just a reminder because I want to do dynamic allocation like always. I want just to spot out the difference between normal using like classic type of array and memory, like dynamic memory allocation. You know, for example, let's say you have an array of results, right? And this is because it is two-dimension. As you see, we are going to have a matrix, and we have I and J. we define it like a two-dimensional, let's say, array. And by having I and j, we are moving to this, let's say, matrix. But one thing I want you to know, I know, in C programming language, you were thinking that we have a two-dimensional, three-dimensional matrix, right? Sorry, uh, arrays. So yeah, everyone knows it, right? Like we have one, like a vector, one-dimensional array, and we have a two-dimensional array and three-dimensional. But in real, in like backbone of computer, there is no two-dimension. Everything is a flat line of the, let me show you. Everything is a flat line of a memory. Uh, this one, this one. Okay, you know, like, yeah, for example, when you see this, you say to yourself, okay, it's like a two-dimensional array. Okay, but in computer, there is no such a thing. In computer, everything is a flat line of memory, and we just access it in a way that we think it is two-dimensional. So we see it as two-dimension, but it is not actual. In for the computer, two-dimensional does not mean, right? So for example, when I say first row, second row, or third row, it is like for the computer, he for example, let's say he knows that for example, okay, the dimension that programmer defined is, let's say, 4. When he wants the second row does not exist, but since the length of it's 4, it starts from the 4. So you think it is two-dimensional, but in real life it is not. Why do I say that? Because I want you to understand why, like what we do in the programming when we are working on very, very low level memories. So don't get confused by that. It was just a brief, like theoretical part. We will see it how we are going to do that. Okay. Bring back to our example. Okay. So I say I have a matrix A and I have a matrix 2 and I want to multiply to matrix 3, the result. Okay, so let's say, as you already know, what is the first, it is important for me so you learn the logic. When you learn the logic of CUDA, then, for example, there are plenty of C codes, C examples. You can see them and you can push them into the logic of the CUDA with modification and have your CUDA version. So you can, like, let's say, make C codes applicable for the CUDA as well, if you know the logic. Okay, let's for ourselves, let's allocate memory on our host. So as I like to always put command, I put like allocate memory or matrices, matrix memories on host, right? So A, B, C matrices, like this. Okay, so like always, what we do, for example, we are going to use pointers and do the memory allocation. So I will call the first one, for example, host A, right? And what we are always doing, integer, let's say, as the type is integer, and using malloc or malloc, which is a true form, and let's close the brackets. Okay, so let me put it in there. So basically, if you remember, like for our normal examples, we have a vector which was in a size, right? For example, vector size or something. So let's say I'm going to come back to this one. Let's say I want to have a definition that shows me what is the, let's say, what is the length of my matrix. Okay, so I am going, let's say, we call it n, or we call it, I don't know, whatever. So I put some definition here in the beginning. I go here. So like always, let's define. You remember we will define vect size or something. I'm going this time to put n, let's say, and this n would be what? Would be my dimension of the matrix, and let's put it, for example, 4. Okay, so 4 would be the dimension of the matrix. So when on the memory allocation, I know how much should I allocate. And let's, now we are here, let's define our block size as well. So you remember, like as always, block size. This time I will put 32, for example, just to see. Like later, but we will learn how to put an optimum one. But for now, pay attention on this n. N is the, let's say, the dimension of my matrix. So here, when I'm going to do memory allocation, I know how much memory should I allocate. Okay, so you remember when we had vector, we will say like n, let's say, or vect size multiply to size of, for example, int. Remember, we were doing that because it was a flat vector. But here, let's see the image again. See, here we have n multiply n because it's two-dimensional. We have n in n. So am I clear? You see, for example, we have not only n because it's not flat. When I say n multiply to n, it will be equal to this. So good idea, right? So for memory allocation now, just rather than n, since I'm going to work with two-dimensional, I would say n multiply to n to the size of int. It means I have like an equal to a two-dimensional memory. So I'm going to replicate it again for the second matrix, which is B. Here shouldn't be changed. And the third matrix, which is C. Okay. So now I have, like, let's say, three memories for two-dimensional matrices: matrix A, matrix B, and matrix C. So I'm going to randomly generate, like, fill the A and B, because A and B are the matrices which I have, right? So for sake of this, I'm going to just use a for loop. Okay, I'm going to fill a matrix. So basically, I'm going, let's say, write C out. I'm going to write mat. I'm going just to basically to fill with the random numbers each two matrices. Okay, I will call it like matrix A, and let's say, and then go to the end line. So basically, okay, I wanted user to see what was the random value. Then I'm going to, like, a for, like, two-dimensional, because I have two dimension. So I will say, like, for example, int row equal to 0 to row less than what? The dimension I have, plus row. Okay, this is it, and then open the brackets. Okay, so again, it was for row, so let's do it for the column as well. For int call equal to 0, call smaller than n, same thing, plus column. So this is for now. Again, open these beautiful brackets. Okay, so I'm going to fill my my matrix, right? So in normal, let me show you, like, in normal way, and let me show you then what do I mean by that. For example, in normal memory allocation, when you define, I want an array of this size, you say, for example, h underline a, and it would be, let's say, I or j, or in this case, it is like row and call, and then you were filling it with something, right? But here, as I said, we don't look at it like this here in this case, because, as I said, we are seeing a memory, like, dynamically in a flat line. Okay, so basically what I do is I'm just, rather than this, I am just multiplying row to the size of the dimension of the matrix, and then plus column. Okay, and I'm going to fill it. Filling with what? Okay, I said I want random numbers, so I need a library here. Let me put it here. I think, yeah, include mat.h. Oh, yeah. I like it to put it like this, mat.h. So this library provides some functions like random, which gives us ability to fill uh, matrices or whatever we want with uh, random numbers. So I just put rand, and the amount of random number would be, for example, let's say we want it for between 0 to 100, between 1 to 100. So if I here put like here, so now it will be randomized. Here in this case it would be from 0 to 99 because it starts from 0 plus 1. Now it would be like from 1 to 100. Okay, so I just want you to understand this part, row. Let me put it there because I want you to understand it. I am going to put it here. So you see what I did? The dimension is n, right? So each time row multiply to the n. The first time, let's say we are on the and we want to access to these memories, right? The first time the row is 0. Okay, so everything multiplied to 0 would be what? Would be 0. Okay, then we have 0. Then column, which is this will go from 0 to 3. So first one would be this, 1, 2, 3. For the second row, now we are going to stop here because now row is 1 and n is, let's say, 4, right? So we are going to stop here. And again, so it will be always 4, like it's like a base. It starts from here, then column 1, 2, 3, 4. For the second row, because this time 2 is multiplied to the dimension, we will stop here. And again, column 1, 2, 3, 4, and so on. So as you see, in real life, we don't have 2 dimension. We only have 1 dimension. I know you see in programming like I and J, but that will be even translate to this, which I'm telling you. This is the lower level. So that's why I am filling my data like this. And let's show to the user that what I just like randomly grab. Cout and HA, the same thing. Row multiply to n plus column, and put a, let's say, a comma between them. Okay, so basically we filled matrix A, and we show to the user what is it, and so let's put an inter between each line so it looks like a real matrix. So I will just put like a cout again here and line. Yeah. So as you see, once again, we create a matrix memory and we fill the memory. And I told you how it is basically a flat memory. And we think it is 2 dimension. And this means like this. We filled it with a random number between 0 to 100. And I just put this for separating between the numbers to show to the users. And then hit enter after each line. Okay. I'm going to do the same thing for matrix B as well. But of course, I don't want to repeat what I just said. I'm going here and I'm copy pasting it. So, yeah, since I'm a Python user, I always like everything to be aligned. So forgive me for that. So here would be matrix B. And again, This is the same. This is the same. Just here, HA will be HB. Just the same process, but for the uh, second matrix, right? So, and so you understand what I did just up until now. I filled the two matrices. Of course, I don't want to fill the third one because the result is going to be on this. So it's like nonsense. So at this step, again, see the logic. I allocate memory on host. Now I'm going to allocate memory on GPU, or let's say device, as people say. So allocate memory on device. Again, GPU. So you remember how it was looked like, right? So it was just Cuda malloc, but you remember we had something that we like to put everything inside Cuda check return because to understand the errors, right? So let me put some spaces here. Okay, then Cuda malloc. So basically here, I want to allocate the same memory on the host. But let me define it. I forgot to define them first. So I will define three variables, just like what I did. For example, this time device A and device B, let's say, and device. I hope I don't have any typo. Okay, so I define three of them. Of course, you can like put each of them equal to null, but it's not necessary. So yeah. So this is the equivalent to these guys here, and I'm going to allocate memory. Okay. So this time I will put the address of the DA, yeah, device, and the size would be just like these other guys. So I'm going to copy it here. See, because size should be equal, as you know. So basically just like this. Yeah. Okay. So I'm going to, I don't know what I'm getting an error. Let me see. Check macro here. Okay. We will see if we get an error, we will see. So let me, if I had enough parentheses, 1, 2, 1, 2. Yeah. Okay. So I got the first memory allocation here. And again, Cuda check return, Cuda malloc. This time address DB and multiply to n, multiply to size of int, going to close it, going to close it, going to close it. I got what was my error, one missing parentheses. That's why I wrote it again. Yeah, these things happens. So let me do it for the device third matrix as well. So as you see, I defined it here. I allocate memory here. So what would be the next stage? So as you saw, I have two matrices here, which I feel I have three matrices here. So let's copy from host to the device. Again, this is the logic. So copy from host to device. Okay, so as you know, the Cuda copy process is like Cuda mem copy and destination device A, because we're going to copy there from host A, and the size is like again n plus multiply n multiply size of int. Yeah, so that's it. So this is it. And oh, sorry, I forgot to put direction. We have to put a direction as well. So I would like Cuda, uh, sorry, Cuda, mem copy host, yeah, host to device. Yeah, so as you saw, it shows the direction just as a repetition. This is the destination where we want to be copied, which is device, from host, which is this one, this size of data, the direction. That's it. So, and then I will put it. And let's put this inside our Cuda check return. Sorry. Okay. Also, I want to do this for the second matrix as well, right? So instead of this, I will put like device B and host B. Okay. So what these two lines do, you see, the logic or the workflow is repeating and repeating over and over. So again, now I'm going to define my block size and grid size. So I would just say like define, sorry, see, Python user. I just wanted to put comment like this. Okay, define block size and grid size. Okay. So again, just as you remember, like last time, we will have like integer our block size, which is equal to block size which I defined above. If you remember, it was 32, and the grid size, size would be, for the sake of consistency, I will put it here. We have a formula, if you remember. It was just like, for example, we on our previous case was vector size plus block size minus 1. Here it would be n, because the dimension is n. So n plus block size minus 1, sorry. We were doing that because we know that division in C is like just gets the smaller number. We wanted to fix that problem, which I explained in the first week. So this is block size and the grid size. So this is what you already know. But one thing here I want you to know, and that is here, since we are going to have, some of you might have this question in your mind that, okay, here is this, but this is like 2-dimensional, and is just the, let's say, representer of 1 dimension. That's why there is a method, like in Cuda, there is a struct called dim, okay? And in this, or dim tree, in this dim tree, you can define block size and grid size with dimensions. Cool, right? So on the previous part, like previous weeks, we didn't need that because it was just a flat line. But here we have a 2-dimensional line. So let's say I will just put a comment, and I was like using dim tree, which is a struct, to define dimensions of block and grid size. Okay, so the struct, you already know C++ and C is already predefined for Cuda, and it's called dim tree. It gives me the ability to define blocks and grids in dimensions. So I would say, like, for example, I call something called blocks because it's dimensional, right? And this time I will put the dimension I want. So I already defined here, right? But it is 2-dimensional. So I will say block size to block size. Block size. Okay. So basically, I'm just making my dimension like 2-dimensional. You see, it was 1 dimension. Now I'm using like a this struct to make it dimensional. Again, the same thing applies for the grids as well. So grids, it would be this time grid size to grid size, of course, grid size. So I know sometimes like some logics are different and for you, but as you see, like it will repeats and repeats again. Now you know, for example, the like copying host to device, allocating on host, allocating on device. These would be just like after a while you will learn it more and more, and it will stick in your mind. So now we can launch our kernel, right? By launching our kernel, I mean, like, for example, the thing that we were doing, like, as you remember, like, for example, we have a function, let's call it, I don't know, now it does not exist, like matrix, for example, mult, or, yeah, matrix mult. And you remember we had these three, and then we were defining, for example, grids and blocks. And then we will have our inputs, right? So before I will put input later, but before that, let's say I'm going to run this, but it does not exist. So let's define it first. So as you remember, the logic is the same. I'm going to use global memory. So I will just simply go somewhere and we're going to define my global. This function which I'm going to use basically. So because it's going to be global, yeah, global void, the name I just create for some reason, yeah. And so the input would be, just think about it, it would be two matrices and the third one for the result, right? So I will put like just int star a, which is a pointer for first matrix, int star b, a pointer for the second matrix, and int star c, a pointer for the third one. Okay, so basically that's it. So and I'm going to define my so let's as now I know what should I put here. So here I'm going to send what. So basically it would be uh, device. For example, the first one is like device matrix A and device matrix B, and of course device matrix C. So see, program tells you like what to do at the, so because I put this, so okay, come back again to writing. So now I know that I have to fill this because I'm going to set device A here, device B here, device C matrix here. Okay, so what to do? You remember like before that we were getting the like the threads number. You remember? So here we have to do the same, but with a small modification. You remember, for example, before that we were using like for example I or whatever, for example int I, and it was equal to, let's say, block id x dot x, and it will we will multiply to the dimension of the block sorry, block dimension this times x, and we will we will just add it to the thread ID, right? Thread ID x. That's x. So we were doing that if you remember, okay? But that was one dimension. Here we have two dimensions. So let's see the photo, and we can have like better understanding again. So as you see here, so what do I want to do is basically, let me show you. Okay, you remember the matrix, how it was multiplying? Here I just, each thread will be responsible for getting one row and one column and multiply them together and put it on the correspondent cell in the third matrix. So that's what the each thread should do. So each thread gets like 2 lines from corresponding matrices and multiply them, and so and doesn't care about the other. So you don't need like a loop in loop in loop for taking care, for going from these to these to these to these. So you don't need to do that. Just we only get the one ID, and each thread is going to just do its own job. But as you see, here we are in the two-dimensional space, let's say assumptional two-dimensional space. So we don't have only just X, right? We have Y as well, because our matrices has X and Y as well. It's like two-dimensional. So basically, what do I mean by that? I mean, this is not enough. We need another identifier for another dimension as well. So as you know, for example, here, when we go here, we are going to the columns, right? Column 1, column 2, column 3. So when I'm going through the X, I'm getting basically the column. So here I put this one, name this one column. Okay, I need this one as well. So when I'm going through this column, I'm changing the Y. You see, Y here is changing. So I'm going to do the same process, but here. So for row, you see, for row, Y is changing, not X. So I'm calling row. So again, block ID X, this time Y. See, the difference is here. And the same thing, block time Y. Let me put it here. And again, the same thing, thread ID X dot Y. So you understand from the photo, why did I do that? Because just knowing X is not enough. I have to know these as well. How to get these identified? Because I want each cell to get from one row and one column. Okay, how do I get it? With this, just changing rather than X, get the Y. So that's it. So the difference here is this. So let me put a comment for myself to remember. I will select compute. For example, each threads, let's say global row and column. So this will repeat us again. Column index. And as you remember, on normal one, this one was enough because we have a vector. Here, no, we have two-dimensional. Okay, so now we are going to calculate our value. You remember, just like this, okay, just like this. With the flat memory, I'm going to do the same. So first, I need a for loop. And again, I will call it, let's say, integer, like just normal for loop, like k or whatever, counter, whatever value you want. And while k is smaller than, of course, the dimension, and plus plus, or k plus plus, k plus plus. Okay, so yeah, that's it for our loop, and let's fill it. So remember, just like the last time, here I'm going to like do the summation. I'm going to do this thing here. Okay, so let me to have the photo again. I really like this photo because I want you to see what I'm doing basically. So this photo is here. Okay, so I'm going to fill only one cell as a result, right? Let me put another photo as well. Yeah. So as you see, I'm just going to fill one of these, and it gets these and these. The length of this k will take care of it. K goes through all of these. So basically, then I'm going to fill matrix C, right? So I'm saying like matrix C or whatever name you chose, then row multiply to n plus column. This is what I just did here, and I explain why. Because basically it is a flat memory, right? So I'm doing that, like getting this, and it is, let's say, equal to its previous, because I'm going to just sum all of the multiplications. So I will do it like a plus sum. So what? Matrix A, this time row, again multiply to, let's say, here is like n, this time plus our loop counter k. Okay, so it gets, for example, each time this row, and so we are going to multiply them to the correspond in the b. Again, it will be b, this time k, because now we are going to on the y-axis. So I put capital K. K, this time multiply to n, which is dimension, plus column. So that's it. Okay. So basically, what is do here is like it gets corresponds value and plus it each time to the cell. So like after all, when it goes through all these k, it has the all values calculated here, because k goes through the n, right? So dimension. So I already explained to you why it is like that, as I said, because it is like flat memory. So and by now let's put this value in the beginning to the 0. So maybe like at first it is some funky number which I don't want to mess with my number. So yeah, initialize it to 0, and that should be it. So as you know, only we are going to fill this again, and we are going through one row and one column. So this is basically this cell, and we are going using k. We are going through this and through this. This multiplication and column is because in real life this is not two-dimensional. This is a flat line. Okay, so that's it. Let me close it as well. So I hope I didn't miss the function by now. Okay, so we have defined it, right? So here it is going to be run, and as you see, we are going to run it, and just like always, waiting, we have to waiting for synchronize. So waiting for, I'm repeating it because you understand the logic, GPU to be finished. And for that, what we have done, we are doing Cuda check return, which is okay. So what we are doing Cuda device synchronize. So Cuda device synchronize. I hope I don't misspell it. Yeah. Okay. So we are waiting for the GPU to be finished, just like always, and so on. So now it is finished, right? What to do now? So let's get the results and copy it to our host C, to this guy. Okay, so we have to get this guy and copy it to this guy. So again, we are going to use this memory copy. For the sake of speed, I just copy paste this one, and let's say here, and of course I'm going to change it. Copy back the result from host, from device this time, device to host. So what we are going to, this is the destination. So device C, host C, right? And this should be changed, of course, because this is host to device. Now this is device to host, just like the tasks you already did. So now we are getting back this to uh, our memory. And now let's print stuff. So for the printing, we were going to use what we just already create. I don't want to repeat what I said. So basically, I'm going to just show the user what is the output, right? So here I would say matrix C, or let's say result, okay, something. And again, this is a for loop, goes through the end, but this time we are not going to fill anything. So I'm going to delete this line and C out C this time, right? So I'm going to just, this is just going to print everything for us. And of course, the last stage for us, let me put comment here, showing the result. Yeah, I really like commenting. I want everyone to get this, like, let's say, habit. So now we are going to free everything we just uh, used. Free memory, memories, because I want to free everything. So again, Cuda, because I'm going to check return. So Cuda free, Cuda free. What I'm going to free? DA. Okay. Okay. Now I'm going to repeat this. Device B, device C. You see, this is the same. Like, so you get the logic. And again, free, this time host A. And copy, host B, host C. Okay, now, so the logic is the same. So let me repeat once again the right logic, what we did. We allocate memory on the host. We fill them with the random number. We understand that in real life, memory is just a flat line. And then we allocate memory on the host, sorry, on the device. So what we want to be copied to the device, we just copy using these two commands, like from our computer to the GPU, copy with this guy. We choose the block size. We learn for the two-dimensional, we have a struct we can use. And then we define the global function on GPU to be run on GPU. And we send information to them. And we wait it to be finished. In the meanwhile, this guy calculates the values. And as you see, you learn that it is not going to be always like this X. Sometimes we have a two dimensions and we get the second dimension like this. And then we calculate this using the logic I already told you. And then go back. Then we copy back the result and we showing the result to the user. We free GPU, we free CPU, let's say. Okay, usually when you write everything like this and don't compile in the meanwhile, it's like a huge chance for everything to get some errors, but let's don't care and wish you will see. So I'm going to create a new folder and I'm going to call build just for the sake of consistency, and name, as you see, ls. Now I have a build folder here. I'm going to inside my build folder, just to repeat everything. Here you can on the CMake list, you can name the project. I just name it code, just because I want you to understand. You can change it and save it, of course. Okay, go back to the code. And here using CMake, I'm going to CMake double dot. It gets this num guy. And let's see, finding compiler, finding. Okay, let me, this is just a moment. Okay, okay, so we just did CMake. And now we are going to make here, if we have some error, it will be shown. I wish not. Okay, Thanks God, no. So you see, build target this time code. This time code because I changed because some of you asked in the previous week. I just wanted to be repeat. Okay, now I'm going to run the code. Okay, you see, this is the first matrix, which is 4 in 4. This is the second matrix, which is 4 in 4. But I have gotten like an invalid argument in line 103. Let's see, what is this guy? I think I forgot to add something, which I just remember. Okay, yeah. Cuda memcopy. Okay, let's see if it has a problem here. Cuda memcopy. Device C. Just copy back the result from host C, from device to the host. Okay. 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 I got what I made mistake. You see, here I'm going to copy from device to host, right? Device to host. Here is destination because I just copy pasted. So lesson learned. Never copy paste everything. It should be host C. It should be device C, right? So let's make again. Let's run the code. You see? Now it's as you see, it's matrix A, it's matrix B, which just generated randomly. Each number, we have a 4 in 4, each number between 1 to 100, these two guys. And then we have a matrix result, which is equivalent to this. Okay, just one thing I want to mention, which I remembered I didn't add. Here, in this case, there was no problem because of that, but it could have caused some problems. You know, I didn't put any boundary on my global, let's say, on my function, which is going to be run on GPU. What do I mean by that? I mean, if for example, sometimes some cells are not going to be fit, which we shouldn't calculate them. We shouldn't like use those memories which are more than the dimension of my matrix. So I have to usually add a boundary. You remember we were doing it in our previous examples as well. So I'm going to add a boundary, which I mean like if the row which I'm getting here or column both, for example, row was smaller than n, because I don't want to surpass for the bigger numbers rather than dimension of my matrices. In some cases, like here, might not cause problem, but it could cause problem. And also column smaller than n. So do whatever you're going to do only for these smaller guys. So that's it. It's just like extra cautious, which you have to do. Always found a boundary that, for example, as I said, sometimes your dimension is could be too big or too small. This will take care of that. So let me save it and again make it and again run it. So that's it. That's it. It was matrix multiplication. And for me, it was important for you to understand that each, let me show you the image again, that each cell on the dimension is responsible for just one value, and it should get one row and one row. Since it was not just a vector, you have to get you have to get here using y dimension as well, rather than only x. And other thing that I wanted you to understand is, like, for the computer, there is no actually two dimension. It is all flat, but we can access it the way I just showed you. For example, as you see, like row to the dimension. So dimension of, like, if it's two dimension. So the first time it is 0, the second times it will start from here, then column will go to this. The third time it will start here. I mean this guy. And you go through this time and this. So basically it is just like a flat line. You see it like this. So that was multiplying two matrices, two square matrices using global memory. Of course, shared memory is another thing. We will like cover those in future. And for now, it's just enough for you to grab this. And do you have any question in this regard? Okay. Of course, if you have if you have any questions, you can like directly message me. And I know it could be sometimes like confusing to get in the beginning, and I just try to start everything from the scratch. And the concept is important for me. That's why I'm repeating the concepts usually. I just wanted to show to see, because usually, for example, I don't know, you just say int, I don't know, a like this, and you usually define memories in similar ways based on C or C++ you're using. But here we were using dynamic. I wanted to show you when you use this, even like for the computer, it is basically this. You just don't see it. Computer will take care of it for you. But we are doing this manually, and because we are on the low level. So that was this, and so yeah, uh, that was some example of using matrices. And of course, we can like increase the dimension to like as much as we want. But for calculating image, for example, especially if you are using on image processing, like huge image processings, GPU will come in handy for you. Of course, but for example, in Python and in these high-level languages, if you're using them, they automatically do these things for you. You don't have to do like too much. They automatically manage your CUDA and everything. But of course, when you really need a speed, you have to do things manually, and it would be way faster than Python things. So of course, a bit maybe you might sometimes you want to put your computer out of the window, but it worth it for the real cases. So that's it. So I'm waiting for questions. If anyone, I just gave some time for you to think. If you have some questions, and as I said, if you want, you can later like message me, and we will have time directly. So okay, if no one has no more questions, I am closing this session, but I will be here for half an hour. And like previous week, if you have any question, you can directly text me, and we will have a direct contact. Okay?
Okay, sir.
Okay, thank you. So thank you for the time. Thank you for paying attention. And I will be here. I'm just closing this connection. So for those of you which are going to go, have a good weekend. Bye.
Goodbye.